Our speaker is Joerg. I hope I pronounced your name correctly.
Yeah, perfect.
Okay, and he's from University of South Alabama, and you know, I just know him some months ago because we joined the editorship of the Alabama Journal of Mathematics. So yeah, I'm very glad to have him here. Thank you, Joerg, for joining us. And I think we have very good colleges and friends in here from from different universities and from Vietnam too. So I'm very happy. Now I would like to suggest Ken to say something about the seminar before we start.
Sure, thank you. Well, welcome everybody. Hi, thank you all for attending today's inaugural Trojan seminar that's virtual. And this is, and I know most of y'all, maybe a couple I don't. My name is Ken Robley. I'm a professor and chair here at the Department of Math and Statistics here. We are officially Math and Statistics now at Troy University. And thank you in particular to everybody for attending today and supporting the seminar. And thank you, a special thank you goes to Dr. Dean for organizing this and for getting us all together. So this is quite an achievement. It's a good opportunity for all the faculty and students here today and in future seminars too, and spread the word too if you have anybody else that might want to join us to share their research with others across other universities, and not only in the state of Alabama, which is usually our focus at the seminar, but now we can go to different universities across the country and across the world too. I see. So this is welcome everybody, and then maybe it's a way we can build possible collaborations as well. So it is especially a nice way, as already been mentioned, to connect during the pandemic. You know, so it's a good thing about the technology we have here. I look forward to the talk and future seminars, and so welcome and thanks everybody.
Please, you can start your talk right now. And by the way, if you have any questions, please you can. I think you can stop the speaker anytime, right?
Yeah,
with
that's
questions.
Right. Yeah.
Or if you want, you just type your questions in the conversation box, and then we will discuss about that at the end of the talk. Okay.
First of all, thank you again for the kind invitation. I'm supposed to say a little bit about the Alabama Journal of Mathematics at the beginning before I come to my talk, right? So in April, I was elected as a managing editor of this journal, and together with the editorial board, who is one of the members, as you mentioned already, we would like to make it more visible also outside of Alabama, but in particular, we would like contributions from people within Alabama. So please look at the webpage. I updated it quite a bit. I've reformulated the aims and goals, and we are very broad. In particular, we also encourage student research papers. Yeah, so I have it's quite broad what we have in mind, and of course we need contributions. Otherwise, the whole thing will not fly, right? So please, yeah, if you are interested, it's a peer-reviewed, freely accessible electronic journal, so everything is available on the web page for free. So that's a good thing, I think. Yeah, but we will see. Yeah, and one goal is to make the quality better, that it might be appear in mass reviews and so on, that the quality becomes a little bit higher. I don't want to say the quality is now not good, but apparently the journal is not widely recognized, and we would like to improve this. Yeah, so I'm more than happy. So all the contributions go to me. Yeah, so and I will then look for reviewers, and then we will, the board will make a final decision after that. So let me stop sharing this and then bring up my talk. Yeah, so what I would like to talk about today is something from linear algebra and the connection between certain structures. Yeah, I want to talk about vector products and division algebras. So let me give you first an overview of the talk. Maybe I'm a little bit too ambitious. Yeah, it's a lot of material. So in the next slide, I will give you an overview. And if you know what the things in the slide are, then you have already heard the whole talk. But of course, I will afterwards go into details. Yeah. So the talk is about vector products, as the title says, and I go quite a bit in detail into vector products. That's something that unfortunately is not taught anymore a lot in linear algebra classes, but it's a topic of linear algebra, of course. I mean, I only teach it here when I start teaching calculus 3, multivariable calculus. The only time my students see vector products, as far as I know. Yeah. That's a little bit a pity. I think it should be a topic of at least linear algebra 2, but I think it's not even in the textbook. I didn't teach linear algebra for a while, but if I remember it correctly, it's not even in the current textbooks, at least not those that I am aware of. Yeah. And in fact, vector products are very interesting in some sense because they don't happen very often. They only happen in certain dimensions. And that's the whole goal of this, this talk. And in fact, the surprising thing is they are connected to some other algebraic structures, namely composition algebras and alternative division algebras. And in some sense, all these three things are the same. That's in fact the main message of the talk. Of course, some of you might not know what composition algebras are. They come from number theory. I will explain this in detail. Yeah. Now, this is exactly the overview. That's in principle the whole talk. Let me explain a little bit, and then afterwards I go into the details. So the first object I will talk about are what I call vector product algebras. Yeah. So it's a vector space and a Euclidean vector space with a vector product. Yeah. And of course, the product has the properties of an algebra. That means the multiplication is compatible with the addition and with the scalar multiplication of the vector space. That's called in general in abstract algebra an algebra. And there are two other structures that are closely related, namely composition algebras, and I will explain in detail later. And one correspondence to vector product algebras in the sense, if you have a vector product algebra, you get a composition algebra. And in fact, it has a two-sided unity element, that's the unital. And vice versa, if you have such a unital composition algebra, you can construct a vector product algebra. Yeah. So therefore, these two things, so if you know all the vector product algebras, you know all the unital composition algebras. And you might have seen in my topics list the notion of a mutation. You can use this tool of mutation to go away from unital composition algebras to any composition algebra. And there's a very famous theorem of Hurwitz from number theory, which classified all finite-dimensional composition algebras over the real numbers. And in fact, I will only talk about the real numbers, but you can do everything about any field as long as the characteristic is not 2. I think you can also do it for characteristic 2, but then you have to do some special yoga, which I don't want to go into it. And it turns out then, first of all, it will turn out that vector product algebras are always finite dimensional. In fact, there are only 4 dimensions where vector product algebras exist. The same for unital composition algebras then, by this correspondence that I just mentioned. Yeah, and it turns out that finite dimensional unital composition algebras are alternative division algebras, but it also turns out, and alternative is just a slight generalization of associativity. The most famous example, a natural example, are the octonions, Cayley's octonions, right? They are alternative but not associative. Yeah, and in fact, these are, yeah, Cayley's octonions are alternative division algebras, and they are also, for the reason I just indicated by the equality sign, they're unital composition algebras, and they give rise to 7-dimensional vector products, and vice versa. Yeah. So in some sense, this is all about octonions, quaternions, and so on, yeah, and behind. But in principle, I mean, you don't need really this. This is just what falls out, yeah. Okay, and in fact, there's a famous theorem by Max Zorn, yeah, which was proved much later than Hurwitz theorem, which says that every alternative, finite dimensional alternative division algebra is either the real numbers, the complex numbers, Hamilton's quaternions, or Cayley's octonions. Yeah, but this is also equivalent by this correspondence that I set up here to the fact that vector products only exist in dimension 0, 1, 3, and 7. Yeah, so that's the whole story that I want to unfold now. Are there any questions so far? Am I going too fast, maybe? If I don't hear anything, I assume it's not. Yeah. So let me introduce now vector products, which hopefully all of you know, but I do it in a little bit more abstract way, of course, than it's done when I teach calculus 3, right? So a vector product, first of all, I need a Euclidean vector space. So it's a real vector space. Everything is over the real numbers in my talk today for simplicity. And this vector space has a positive, definite, symmetric bilinear form, or a scalar product, or a dot product. If you like it better, I also use the dot as the symbol. Yeah, and then this vector product satisfies 4 properties. Yeah, the first is just it's linear in the first factor. That means it's compatible with the vector space operations. Yeah, and then come the things that you also know from, I'm not good in the scrolling. That was my worry. So let me put it, yeah. So the second axiom, or the second defining property, is the cross product or the vector product is orthogonal to the first factor because of the third property that it's skew symmetric. It's then also orthogonal to the second factor. That's also something when we introduce the vector product in calculus 3, we tell our students, right? Yeah, and because I don't want to introduce trig functions, yeah. Remember when we introduce it in calculus 3, right? Besides this orthogonality to both factors, we say that the magnitude of the cross product is the product of the magnitudes of the 2 factors times the sine of the angle between the factors. But I don't want to do it here because, especially in principle, I want to generalize it for arbitrary fields, right? Then I don't have this available. So you can replace this definition using the sine by this equality, right? And I square everything here, and this is just the magnitude is the square root of the dot product of a vector with itself, right? The usual way. And then I can get rid of the sign, yeah, in principle, because the dot product contains a cosine, and I just change things. And I use the squares here just that it fits into one line, yeah? So you can formulate it a little bit easier, of course, yeah, but with just using the dot product, but then the formula is much longer, yeah? So that's for me now a vector product, yeah? It's compatible with the vector space structure. It's orthogonal to the factors. It's skew symmetric. So if you swap the order, you pick up a minus sign. And then in some sense, the most substantial part of the definition is this formula here, which relates the magnitude of the cross product vector to the dot product and the magnitude of the factors. Yeah. Okay, and in a Euclidean vector space with such a vector product, I call a vector product algebra. Yeah, and because Euclidean vector spaces are defined over real numbers, it's a real vector product algebra. So in the next couple of minutes, I would just show you some of the properties you need to prove the theorems I was announcing in the overview on the previous slide. Yeah, so you don't need to understand all the details. It just should give you the flavor of what you have to do. You just do mostly relatively simple computations, except at the end, it's a very long computation. Yeah, when you really want to prove the theorem that vector product algebras only exist in these 4 dimensions I mentioned, 0, 1, 3, and 7. Yeah, so, okay. So I just list a few properties that you all know, right? I mean, of course, the cross product with a vector and itself is 0. Then you have this triple scalar product identity, so you can move the scalar product over, right? So yeah, so the V goes over to the right here, and then it becomes a cross product and so on. Yeah, that's a very useful property. I indicate here the proof, but don't look at it even, yeah, at the moment, because these are too much details, but I put them in here, yeah. So these are two properties I will use in the following. There are some more, yeah. I do this on purpose. You don't try to memorize the properties, but there are some. This is a very important one, yeah. Some of you might remember linear algebra was introduced in an abstract way by Hermann Grassmann, yeah, in the late 19th century. And so there's an identity which is named after him, yeah, which he, I think, also found first. But it's a little bit stronger than this, namely the Grassmann identity has three different vectors. If two of the vectors are the same, then you get this. So you can express a cross product of three vectors if two are the same by using the dot product, or the, yeah, that's what it is. And this is very crucial, yeah. Unfortunately, the Grassmann identity that he found is only true in dimension 3, right? Yeah, and I will come back to it later. Yeah, but so for most of it, we need this. It's enough to have this, what I call the weak Grassmann identity. Yeah. Okay, so. And in fact, it's equivalent to this. Yeah, so you can buzz it up a little bit. Yeah, so if you have three vectors, but then you need two terms in order to express it, the triple vector product identity. Yeah, they are totally equivalent. Yeah. Okay, and then from this you get this, which is very, I call it skew associativity, right? You can move the parentheses, but if you do it, you pick up a minus sign. Yeah. So vector products are, in my opinion, the most important property of vector products. You can orient space, right? This is also how we use it in calculus 3, right? And therefore signs play a big role here. Yeah, signs show up all the time, and therefore you also see if you have a field of characteristic 2, of course, the signs will disappear. Yeah, so it's very important that you can divide by 2. Yeah, or that minus signs show up for most of this stuff. Yeah, yeah, but this only holds if two of the vectors are orthogonal to each other. Yeah, then things simplify. Yeah. And you see this immediately to give at least one proof, right? You see all the three dot products that show up here in this triple vector product identity. If the vectors are pairwise orthogonal, vanish, and then you have the sum of these two products is 0, and then if you move this guy to the right-hand side, you get exactly this. Yeah, so it's not so surprising. Yeah, but okay. Yes, so now I want to move towards the proofs that vector products can only show up in the 4 dimensions I mentioned before. So I need a few concepts, right? So a vector space is a subalgebra if it's closed under the product. That's not so surprising. And then I need a little generalization of what you would call an algebra an ideal, right? If S was the whole vector space V, you would call it an ideal, but I do it for any subset of V. Yeah. So if a subspace is invariant under multiplication with vectors from this subset, then you call the subspace invariant under the subset. Yeah. And of course, a vector space is a subalgebra, yeah, vector subalgebra or closed under the cross product if and only if it's invariant under itself, right? Yeah. So, okay, and now comes two crucial lemmas. The first is relatively easy. So if you have a subset of the vector space and a subspace, yeah, and the subspace is in the invariant under S, then its orthogonal complement with respect to the dot product is also invariant. Yeah, and you use the defining one of the defining properties of the vector product, right? It was the skew symmetry, and then you use the identity 2 that I showed you earlier, right? That you can move over the dot, that it's an invariant form. You could say it's an invariant form, right, under the cross product, yeah. Okay, but that's the real crucial thing is this lemma, which maybe I should explain very, very slowly. Yeah, so now we assume we have a vector subalgebra W, and we have an orthonormal basis with respect to the dot product of this subspace. Yeah, and if we take now, in addition to this orthonormal basis, one vector from the orthogonal complement of this subspace, and I cross, yeah, I take the vector itself and I cross every member of this orthonormal basis of the subspace with this vector, yeah, then this whole set is still in the orthogonal subspace. And these vectors are pairwise orthogonal and have the same magnitude. Yeah, so in particular, if V is a unit vector, yeah, then all these vectors are unit vectors. They are pairwise orthogonal, so it's an orthonormal subset. And the crucial point is I added one vector, right? The subspace has dimension m, and now I have a subspace of dimension m plus 1 of the orthogonal subspace. And this is really the crucial lemma for everything else. Yeah, this is the lemma. So what I do, yeah, I make a subspace bigger, and then at a certain point I will see it doesn't work anymore. Yeah. And I will show this to you in detail, yeah, how this goes, yeah, when I do the proof. So let me just indicate to you how the proof goes, right? You use many of these identities, yeah, in particular the weak Grassmann identity, also, yeah, that a vector cross itself is 0, and also these other, the invariant of the form, if you want, yeah, and you use also the property that yeah, again, the skew symmetry, I think. Yeah. So okay. So use a lot of properties, and if you do it, you see first of all, oops, it goes even further, right? That these vectors are pairwise orthogonal, and you can compute its magnitude by using the axiom or the property for the magnitude. And you see, yeah, if you cross with these unit vectors, yeah, pairwise orthogonal unit vectors, the magnitude doesn't change. Yeah. So all these vectors have the same magnitude as the original vector that you add. And if this vector is a unit vector, they are all unit vectors. Yeah. So this is really the crucial lemma. Yeah. But you see, it's very elementary to prove it. You just use the properties that you have, and then you go through. So now I think we come to the first main result. Yeah. That's the main result from which everything else follows. Yeah. So if you have a Euclidean vector space, yeah, this has a vector product if and only if these 4 dimensions, 0, 1, 3, or 7 happen. In particular, vector product algebras are always finite dimensional. Yeah. You cannot find a vector product for an infinite dimensional vector space. Yeah. But even more so, you cannot even find it for a vector space that has different dimensions than the 4 that are given there. Yeah. Okay. Yeah. I will not go too much into the details, but of course, 2 of the cases are totally trivial, right? And we are not interested in it. If the vector space is 0 or it's one-dimensional, right? The only cross product you always can find, yeah, is, yeah, the cross product is 0, right? So that's, yeah, you have to, because the second vector, if you have a second vector, it either, anyway, everything is 0, or the second vector is a scalar multiple of the first vector. And because of property 1, that V cross V is 0, and it's compatible with the scalar multiplication, right? It has to be 0. You have no choice. Yeah. So these 2 dimensions, in some sense, are not interesting, right? We never, yeah, also in linear algebra would consider it, but still, these cases can occur. So the only interesting ones are 3, which we are interested in calculus 3, right? And 7 is also interesting. Yeah. But normally we don't talk about it, maybe. But yeah, but it's closely related to Cayley's octonions, as we will see later, right? And 3, of course, this dimension is closely related to Hamilton's octonions. And here 3 are the quaternions. Yeah, I should pay attention what I'm saying. So now let's do the first step. Yeah, so we are done in dimension 0 and 1. So the next possible dimension, just because it exists, is 2, right? So let us assume our vector. Yeah, we have a vector product algebra of dimension 2. Yeah, So I only do this direction. If I have at the moment, yeah, here I did both directions in some sense, yeah, but now I assume I have a vector product, and then in this case, dimension 2, I have to show it doesn't work, right? Yeah. So it cannot be 0, yeah, and there are not enough dimensions for it to be not equal to 0. That's the upshot. Yeah. So what you do, you have a 2-dimensional vector space, then you choose an orthonormal basis, E1 and E2. And then, of course, yeah, by the property of the magnitude of a cross product, because E1 and E2 are unit vectors, then E1 cross E2 is also a unit vector. If it's a unit vector, it cannot be 0, right? Yeah, but because the vector space has dimension 2, this cross product vector is a linear combination of the others. Yeah, and then if you just use the property that, yeah, every factor of the cross product is orthogonal to itself, if you dot this equality, this linear dependence relation with both of the vectors, then you will see that both scalars are 0, and so the cross product is 0, but it was not 0, so you have a contradiction. So in dimension 2, it doesn't work. Yeah. By the way, a similar proof, yeah, I think Hamilton gave when he found out that you cannot extend the complex numbers to a 3-dimensional division algebra, right? And then he found his quaternions, so you have to go 1 dimension up, right? I think this Hamilton was for a long time troubled with this, because it would indeed be very nice to have a division algebra in dimension 3, right? But yeah, but in fact, it's even nicer to have it in dimension 4, because dimension 4, then you can do everything. You can include relativity theory, right? So the quaternions are much nicer than a 3-dimensional algebra, but of course Hamilton didn't know that relativity theory exists, right? Because for the Hamiltonian quaternions, you can take the vector components, the 3 vector components. Normally the basis vector are denoted by I, J, K, right? So you have a 3-dimensional coordinate system, that's the space, and the scalar component, which comes in fact from the identity element, we will see this later, replaces time, and so you can do relativity theory very elegantly using quaternions. Yeah, but anyway, that's just a side remark. Yeah. Okay, and we will see later, of course, that IJK, yeah, this structure comes from the cross product in 3 space. Yeah. Okay, let me go over the remark. It's not so important. So now we know the dimension of this vector product algebra has to be at least 3, right? Okay, so now we pick an orthonormal subset of V, yeah, and take the cross product of these 2 vectors in this orthonormal subset, yeah, and then we get another orthonormal subset, yeah. And now the crucial observation, H stands for Hamilton, is that if you look at the space, yeah, spanned by these 3 vectors, it's closed under the cross product. Yeah. And of course, you have to check this. Yeah, but with the weak Grassmann identity, it's not so hard to show this, right? Exactly what you know from the cross product of the vectors IJK that you use when you introduce the cross product in calculus 3 in your class, right? Yeah. And in particular, the basis E1, E2, E3 satisfies the same multiplication table as the standard basis. Here I write it with the usual cross product. Yeah. So now I have this H, right? It's a subalgebra, but it's in particular also a subspace by definition. Now I take an arbitrary vector and I decompose it in this way, right? Yeah. That's the standard way how to decompose a vector space into a subspace, a direct sum of a subspace in an orthogonal complement, right? This guy is obviously, when you look at it, in the orthogonal complement of H, because if you dot with any of these vectors, because of the construction, you get 0, right? So now we have this, yeah? So V is H plus H perp, right? So now 2 cases can happen. Either H is V, so H perp is 0, then we have dimension 3, right? Or else there exists a non-zero vector in H perp. If it's non-zero, we can make it into a unit vector, yeah? And now the crucial lemma comes, lemma 2, yeah? So U is an H perp. So if we cross our original basis of H, right? E1, E2, E3 with U, then we are still in H perp, yeah? And these vectors are also normal, yeah? And what you now do is the following, yeah? You extend this basis, yeah, by U, the new vector, yeah? I mean, the basis E1, E2, E3, you extend it by U, and in fact, by exactly these vectors, yeah? And then you see you have 7 vectors, right? The original 3 crossed by U, and 1 more because you put also in, yeah? And this is an orthonormal subset of V, yeah? These 4 are orthogonal to these 3 because they are an H perp, and they are pairwise orthogonal because of the lemma, yeah? And they also, and everything is a unit vector. So as a consequence, we have a jump now, right? If we are not in dimension 3, we at least have dimension 7, yeah? And now I do the same game again, yeah? And then I will be done. So C stands for Cayley, yeah? So I look at the subspace spanned by all these, right? Yeah, and I have to show it's a subspace. I don't give the details. I need the triple vector product identity and the Weak-Grassmann identity, yeah? But I don't want to go into the details. And then you do the same thing, right? Yeah, you decompose your vector space into C and its and a direct sum of C and its orthogonal complement. Yeah, same construction, and now the same game starts. Yeah, luckily we are done after that, so don't get impatient. Either C is V, then we have dimension. In fact, V equals C, I should have written, yeah. Then we have the dimension is 7, or else we have a non-zero vector in the orthogonal complement, and of course I can make it a unit vector, yeah. And from now on, we suppose that the later happens. There is such a vector, but we will see it doesn't exist, and then we are done, right? Okay, and this is a little bit tedious and technical, so I cross these 2 unit vectors, U from the previous step, U prime from this step, I get U double prime. And then you can show again that you have the usual relations as for the usual cross product, yeah. And then you have this here, so this is non-zero since the last vector is the cross product of 2 orthogonal unit vectors, and as such is a unit vector, yeah. And now we do the following thing, yeah. I take E1 cross U and cross this with E2 and U and the cross product of E2 and U prime, and then I do it in the opposite order. And in both cases, I get U double prime cross the cross product of E1, E2. And I just mentioned that the last vector is not 0, yeah. And you see here now something happens, right? I get both times the same answer, but these 2, it's skew symmetric, right? If I swap, I should get a minus sign, yeah, but that's a contradiction, right? I get this vector is the negative of this vector, so 2 times this vector is 0. I can divide by 2 in the real numbers, and then I get the contradiction, yeah? So that's, in very rough outline, the proof how you show that only these 4 dimensions, 0, 1, 3, and 7 can happen for cross products, yeah? I think it's very amazing, yeah? I mean, that's not at all clear from the beginning and from the definition, yeah? Here it's a proof, yeah? It's not, yeah? So you have to do a lot of computation, but it's elementary computation. You even can show it to your students, yeah? Let us not go into the detail, just that you see it's not magic or whatever. Second identity is the same, so it's 2 pages that you have to do, right? I will skip over the details. So now the only thing I have to do to prove that my theorem, it was if and only if, right? So far I showed if I have a vector cross product algebra, then I have these 4 dimensions. Of course, for dimension 0 and 1, I pointed already out, if I set the cross product to 0, I'm done. So that's the other direction. For dimension 3, we know how to do a cross product, right? We do the standard things that we do in our classes. So the only thing to finish the proof, I have to do something similar in dimension 7, yeah? Yeah, of course, if I'm in dimension 7, it's as a vector space isomorphic to R7 with the usual dot product. And now I use the familiar cross product on R3, on 3-dimensional space. And I use here the standard vectors that we use in class, IJK, yeah, Hamilton's units, yeah, of his quaternions. And then yeah, I use this vector space isomorphism, right? I use ijk in the first components, and I use a scalar component in ijk in the second component. I use it again, yeah, so I double, yeah, three-dimensional space. So 3 + 1 + 3, this gives the 7. The scalar product, I do the same thing, right? Or the dot product, I take the dot product in the first components, and I multiply the scalars in the middle, and I take the usual dot product in three-dimensional space for the second components. And the vector product, I do a little bit more complicated, yeah. So yeah, I do something like a semi-direct product. I don't want to go into it too much, yeah, but yeah, so, and then you have to check, yes, you get a vector product, yeah, okay. Yeah, so that finishes the first part, yeah. Now I want to go a little bit more detail for a moment in dimension 3 for later purposes. Yeah, but I see already I'm running out of time. Maybe are there any questions so far?
Yeah, I didn't see any question, but you still have time. Yeah, don't worry.
Yeah, I know, but I mean, I should finish earlier than 10 for questions at the end or not? Do I really have to 10 or 50? I was thinking of 50 now when I said I don't have so much time. Can I go to 10?
Yes, yes.
Okay, okay, then I'm good. I'm sorry, that was my bad. Yeah. Okay, so yeah, you might not know, but I am from education a Lie theorist, and in fact, Lie algebras are lurking in the dark and some generalizations. And in the next few slides, I want to talk a little bit about this, if I may. Yeah, that's not really necessary for the purpose of my overview to come to the composition and algebras and division algebras, but it just I cannot resist the temptation. Yeah, I mentioned already in dimension 3, the Grassmann identity can be generalized. Yeah, you have the cross product in this form, yeah, of 3 different vectors, and then you get the same thing, yeah, than we got before, but now we have 3 different vectors on the right-hand side. Yeah, we had a sum of 2 expressions by shifting the parentheses in general, right? But in dimension 3, you have the Grassmann identity, and the Grassmann identity is, in fact, it's quite a long proof, by the way. Yeah, it looks very innocent, but the proof is, I think, 2 pages or so. I mean, it's elementary, but it's not easy. Yeah, but anyway, let us know. But the consequence of this is what is called the Jacobi identity, right? If you add, yeah, this expression 3 times and you permute the vectors cyclically, you get 0, right? Yeah, and in fact, an algebra that is anti-commutative and satisfies this identity is a Lie algebra. And in fact, this Lie algebra has a very special property. It's a non-split 3-dimensional simple real Lie algebra. In fact, it's the Lie algebra of the special unitary group SU2. Yeah. So that's just, I couldn't resist this. Yeah, so in dimension 3, if you look at your vector product algebra, it's this Lie, it's isomorphic to this Lie algebra. Yeah. Okay, so you can say a little bit more. So now what is in dimension 7? Yeah, in dimension 7, it's not a Lie algebra because, as I mentioned, you only have the weak Grassmann identity, and indeed it's called what is called a Maltsev algebra. Yeah, after a very, very famous and very excellent mathematician, yeah, Maltsev, Russian mathematician Maltsev, yeah, who used this in differential geometry and so on, this concept. Yeah, it's a very interesting concept, but I cannot go into the details. So the Jacobi identity, because the Grassmann identity is replaced by the weak Grassmann identity, looks more complicated. Yeah, don't even remember, but this is the identity that Maltsev figured out, and algebras of this kind, so they are skew symmetric and satisfy this identity, maybe one should call it the Maltsev identity, behave very similar to Lie algebras, yeah, and they play a role in differential geometry and so on and so on, yeah. And so the following theorem I pull now out from nowhere, right, by Sagel and Loos, yeah, is if you have a finite dimensional simple, by the way, I didn't say what simple is. Simple means it doesn't have any non-trivial ideals, yeah. So this is in associative simple algebras by Wedderburn structure theorem are just matrix rings over the ground field, yeah. So, and they are similar structure theorems for other structures. And so if you have a Maltsev algebra, which is not Lie, yeah, and you have an algebraically closed field, so I'm a little bit cheating here, but you can generalize this, yeah, then this Maltsev algebra is the 7-dimensional vector product algebra, yeah. So it's again a simple algebra, the vector product algebra. That's anyway true, but also the converse is in some sense true, yeah. So, okay. Yeah, and if you put all this together, yeah, then the theorem, so the dimensions we had already before, right? A vector product algebra over the real numbers is finite dimensional. It's only possible in these 4 dimensions. What is the structure? Yeah, if V is 0, it's just a trivial Lie algebra. If you want, yeah, a vector space as with a product 0, right? Otherwise, you get the 1-dimensional Lie algebra. Yeah, in dimension 1. In dimension 3, you get the non-split 3-dimensional simple real Lie algebra, and in dimension 4, yeah, in effect, these are the octonions, and you divide out the unit, this vector space spanned by the unit element, right? That's the Sagel simple non-Lie algebra, yeah. And in particular, as a consequence, every real vector product algebra is a Maltsev algebra, yeah. Okay, so that's the main result on vector product algebras, yeah, and it has a very strong Lie flavor, yeah. Okay, now let me briefly go over the other stuff. The next thing was composition algebras. Let me first motivate it a little bit, because you might say, why do people consider this? Yeah, a composition algebra is a vector space, non-zero vector space with a bilinear multiplication. So compatible with the product is compatible with the vector space operations and a positive, definite, symmetric bilinear form. Yeah, so you could say it's a Euclidean vector space, yeah, with a product that's compatible with the vector space structure, and the dot product or the form, yeah, is compatible with the multiplication in this sense. A times the dot product, if you want, I use this notation here to differentiate from the dot product. AB dot itself is, yeah, I mean, the square of the magnitude of the product is, if you want, the square of the magnitude of the factor of the factors, yeah. Okay, and why is this important? Yeah, it goes back to Gauss, yeah, composition of quadratic forms. I just mentioned this very briefly, yeah. So if you have a denary quadratic form, right, which is normalized, then, yeah, this product should be again a quadratic form. Yeah, that was what Gauss wanted, and therefore the theory of quadratic forms in D variables is happening. This is, he called this a theory of composition, and I will on the next slide briefly remind you what the number theoretic impact is, if and only if you have a D-dimensional composition algebra. Yeah. Yeah, for complex numbers, for example, if you take the real part of the product of the first factor times the conjugate of the second, you get such a thing, right? Yeah, and related to the complex numbers is this so-called two-square theorem, right? So you have two quadratic forms. If you multiply them, you can express it again as a sum of two squares, yeah? And I indicate even the proof, it's just a computation with, yeah, with complex numbers. But the interesting thing is there's a four-square theorem, which comes from Hamilton's quaternions instead of the complex numbers. And there's an 8-square theorem arising from Cayley's octonions. And it turns out, yeah, in effect, how I set it up from our vector product structure theorem for vector products, these are the only square theorems that you can have. Yeah, so there's only a 2 squares, a 4 squares, and an 8 squares. And that the numbers are one larger than in the vector product is because you have to join a unit element. Yeah. Okay, so that's the motivation. And this is the theorem. Hurwitz, a famous Swiss number theorist, yeah, at the end of the 19th century, proved the following theorem. What I just said, if you have a finite dimensional real composition algebra, then that the dimensions are 1, 2, 4, 8. And notice 1 is 1 more than 0, 2 is 1 more than 1, 4 is 1 more than 3, and 8 is 1 more than 7. Yeah. And in fact, in this, you can prove this theorem by reducing it to this structure theorem. If you have a unit element, your composition algebra has a unit element, a two-sided unit element, then it's isomorphic to the real numbers, the complex numbers, Hamilton's quaternions, and or Cayley's octonions. In particular, unitary real composition algebras are always finite dimensional. And in fact, what I want to explain a little bit, before I stop, this result is totally equivalent to the scarcity theorem of real vector product algebras that we just proved. So this number theoretic theorem, or better, this number theoretic theorem of Hurwitz, can be proved by this structure theorem, and this structure theorem can prove just by linear algebra. I think that's very great. It's great. So now let me indicate a little bit how vector product algebras and composition algebras are related. So let's start from a composition algebra, which has a two-sided unity element. I cannot take an arbitrary composition algebra, and you will see in a moment why. Then I can define a vector product algebra. It has the same underlying vector space. But I take, sorry, that's wrong what I say. I take the orthogonal complement of the vector space spanned by the two-sided identity element. For some reason, this should, here it says, I probably should have put here E, Okay, yes, and of course, the bilinear form is the bilinear form of the composition algebra restricted to this subspace, And in fact, the subspace has codimension 1, as we immediately know, right? Because the orthogonal complement, of this vector space, the direct sum of this with this vector space, one-dimensional vector space is A, right? So it has codimension 1. And the cross product you define as follows: 1/2, you multiply the two factors of the cross product, in both ways and subtract them. In fact, this is sometimes called the commutator in Lie theory, right? So in fact, you take the bracket, if you want, the normalized bracket of this algebra. And if this algebra, the original algebra is associative, this will be automatically a Lie algebra. If it's alternative, it will be a Maltsev algebra. That's the thing behind it. So it's, and let us do an example because it's also abstract. Like, let us take Hamilton's quaternions, right? You have the real numbers, and then you add this three-dimensional vector space spanned by the Hamilton's units, ijk, right? And the multiplication is all the squares are -1, like for the complex numbers for I, and I times j is k, and if you swap the order, you get a minus sign, j times k is I, if you swap, you get a minus sign, and k times I is j, and when you swap, you get a minus sign. You see, you permute these vectors cyclically. And the positive definite symmetric bilinear form is this, as similar as in the example for the complex numbers that I showed you earlier. You take the real part. Real part means really the coefficient of 1, right, for the quaternions, of the product of the two guys, P and Q, and the second guy. The conjugate is the same as for complex numbers. The conjugate of a quaternion is you leave the scalar component untouched, and the other components pick up a minus sign. Okay, so and then of course this complement is exactly this, right? The space of purely imaginary quaternions, and the cross product is your usual cross product relations that you tell your students in Calculus 3, and indeed the vector product algebra associated to Hamilton's quaternions is exactly the standard three-dimensional vector product algebra. If you want SU2, the Lie algebra SU2 that I told you earlier. And you can do the same for octonions and so on and so on. Let me not do this. Let me instead do conversely. We start with a vector product algebra. Then I take the direct product of the real numbers and this vector space. So I add one dimension, and then you use this multiplication here, right? It's a little bit like a semi-direct product, and you see the vectors at the end, you cross them, right? You use the cross product of the vector, given vector product algebra. You have a two-sided unity elements, one, the real number 1, and the 0 vector in the vector space. You have a positive definite bilinear form. You just multiply the two scalars and add to it the dot product from the vector product algebra, and then you get a bilinear form. Yeah. And now I do the example the other way around. I start with the standard Euclidean vector space in 3 dimensions with the standard of orthonormal basis. Yeah, and then the composition algebra associated to this is this. If 1 is 1, 0, and I is 0, E1, J is 0, E2, and K is 0, E3, and then you can check that you get exactly the relations that I had on the previous slide for the quaternions of Hamilton. And so the composition algebra of the 3-dimensional vector space, vector product algebra is the Hamiltonians quaternions. And if you then apply the vector product algebra construction from before, you get back and so on. This is this 1-1 correspondence that I was talking about. Yeah. So let me skip mutations, right? Because it's very technical. Yeah. So mutations reduce this theorem. Yeah, this theorem to this theorem. Yeah, so mutation is just a tool that I can later invoke my linear algebra. Yeah, it's a very important tool in non-associative algebras, but it's maybe a little bit exotic. Yeah, so let me maybe skip over this. Yeah, but it's just one tool you need if you want really the proof. Yeah, so you modify somehow your multiplication, and all of a sudden you get an identity element and so on. It has to do with zero divisors or non-zero divisors and so on. Yeah, so let me not. Yeah, so this just gives you the structure theorem reduces. Sorry, the Hurwitz theorem is implied by the structure theorem. And by the construction I showed you, the structure theorem is the same as the scarcity theorem that I at least indicated the proof earlier. Yeah. Yeah, let me maybe skip this stuff. But the important thing is, yeah, in dimensions 4 and dimension 7, you have infinitely many non-isomorphic, non-unitary real composition algebras. And indeed, I think it's still an open problem to find all of them. Yeah. But anyway, that's just so in the real interesting dimensions 4 and 8, yeah, it gets much more complicated if you don't have the mutations, right? So what I want to tell you by this is, if you don't want to do just linear algebra, things get much more complicated. Yeah. So if you want a structure theorem for composition algebras, even finite dimensional composition algebras, which don't have a unit element, two-sided unit, then it gets hard. Yeah, so that's what this says. Yeah, okay. Yeah, so let me go over all this. Yeah, I mean skip over all this. Yeah, the point is now what I want to indicate in the last minutes. Yeah, I want to show that unitary composition algebras are division algebras. Yeah, a division algebras is an algebra where each non-zero element has an inverse with respect to multiplication. Yeah, so it's a non-commutative generalization of a field. And the intermediate step is you show this composition algebras are quadratic. What does quadratic mean? It means every square can be expressed as a linear combination of the identity element and the element itself. Yeah. And you have to do some computations here. An algebra is called alternative. I mentioned it earlier, right? If the weak associative law holds, yeah, it's a little bit like the weak Grassmann identity two-factor. You can swap the parentheses. You can shift them over if two elements are the same. Yeah, yeah. And in fact, it turns out unitary composition algebras are alternative. Yeah, so. Yeah, I will not go into the details. Yeah, so now we come to division algebras, as I said, a non-zero vector space with a bilinear multiplication such that every zero element has an inverse, or these equations have unique solutions. Yeah, and of course, fields are division algebras. Yeah, if I use one of these 4 division algebras, 2-dimensional division algebras, it's even non-associative, right? Even in dimension 2, it gets already hard. Yeah. If you don't have, and that's what this example indicates. Let me skip it. Of course, division algebras have no zero divisors, and the converse holds if the algebra is finite dimensional. Remember, I should have said it when I was on composition algebras, because of its form, have no zero divisors. Yeah. So if they are finite dimensional and unitary ones are, because vector product algebras are, then you get a division algebra. Yeah. Yeah. And in fact, you get an alternative division algebra, yeah. And alternative division algebras have two-sided unit elements, yeah, and now I go the way back, yeah, they are also quadratic, and if they are quadratic, you can define a form, yeah, they are unital real composition algebras, yeah. So if you have a finite dimensional alternative real division algebra, you get back to a composition algebra, and yeah, with a two-sided unit element, and you do something like this here, you again use some vector space constructions. Yeah, you use the imaginary part, but you define it in a very abstract form, which is a complement of the real part if you want. Yeah, let me not go into this. And yeah, and then finally you get, yeah, the theorem. It was first proved if you replace alternative by associative by Frobenius, and in this generality by Zorn. Yeah, much later, you see, 60 years later. Yeah. Yeah, and there's a much deeper theorem, yeah, and this is the last thing I say, yeah, of Bott, Milner, and Cavere, yeah. If you have any real division algebra, yeah, you get these 4 dimensions from the theorem of Hurwitz, yeah. So, but the challenge is you need a lot of homotopy theory from topology. I mean, yeah, real numbers have a topological structure, right? So you cannot prove that. I don't know whether one can, but nobody knows, as far as I know, a proof just using linear algebra or algebra even, yeah? So our theorem was much easier because it just uses linear algebra, but you need one very strong assumption, namely things are alternative. So I would like to go back to the overview and open the floor. I'm 1 minute late. Open the floor for questions. Yeah. So this is what I try to explain. Yeah. These two are in one-one correspondence. You can go back and forth, and these two structures are exactly the same. They just are defined differently. Yeah. Thank you so much for your attention. I hope I didn't overwhelm you too much.
Yeah, thank you very much, Joerg. I think now it's time for questions, right?
Yes, yes.
Yeah. Please, do you have any questions for our speaker?
I didn't check the chat at all, I have to admit. So if there were questions in the chat, please ask me this again, because I was not able to follow this. Because first of all, I don't even find it here, and secondly, I cannot do two things.
I don't see any question in the conversation box.
Okay, then so please unmute yourself if you have questions. I'm more than happy to trying to answer them.
Can I ask a question, Hoa?
Yes, please.
All right. This is Dmitry Glotov from Auburn. Very interesting talk. I enjoyed it very much.
Thank you.
So the question I have is about the first part in the converse, in the proof of converse of very interesting construction. So I have 2 questions in this regard. So the first question is,
shall I go to the slide?
Please, yes.
Yeah, okay, yeah. So please go ahead. I didn't want to interrupt you, but I.
So my first question is there motivation for this construction? So it's.
That's a very good question.
And the second question is whether this.
I think I'm here now. Yeah.
Whether this is a unique vector product.
I don't think so, yeah, because, I mean, the unique, sorry, these were 2 questions. The second question, I think, is the only one that I really can properly answer, but I will come back to the first question. The second question is not unique. I think you can always you can change things, yeah. I mean, it's not unique, I would say. What is unique is that it's a Maltsev, we're talking about dimension 7 at the moment, I think, right? So it's unique in the sense that there's up to isomorphism of algebras a unique Maltsev algebra. Yeah, and so the vector cross product algebra is always isomorphic to the specific Maltsev algebra that I indicated how the construction goes. Yeah. So in this sense, it's unique, but I don't think the product is unique. I mean, already in 3 dimensions, you have different cross products, right? You can define the cross product in the usual way, or you can define a new cross product, cross prime. You take the opposite order, yeah. Yeah, my telephone is ringing. I let it go. I'm sorry. Yeah, does this make sense what I just said? regarding
Yes, thank you.
question. So it's not unique as a product, but it's unique in the sense if you consider the vector product algebra as a Maltsev, I mean, as an algebra, it is a Maltsev algebra, and it's isomorphic to this very specific Maltsev algebra.
Mm-hmm.
But the first question, honestly, I think I mean, it's not my construction, by the way. So I think you put it together. I mean, what do? You do doubling. By the way, I mentioned a very important person that plays a role here, Dixon, right? Dixon, Cayley doubling. This is exactly what you do here. I mean, you double, in the middle, you take the scalars and you double the first component here to the second component, and then you do everything not quite symmetrically, but mostly you do, right? That's the motivation, I would say. But I didn't invent it, so I cannot tell you what the people who invented it did think, right? Yeah, I mean, the dot product is very easy. Yeah, you just double everything. Yeah, but the cross product, you see, it's a little bit more involved, right? Yeah. I mean, the scalar, I mean, always you take one part here and you go to another part here. Yeah. Yeah, and in the first component, or the first component, you use the cross product of V1 and V2 minus the cross product W1, W2. Here you do it a little bit differently, right? You mix it. Yeah, you go therefore I said semi-direct product. You go from this cross this minus this one cross this. Yeah, and with the scalars also, you mix the scalars, right? This scalar from the first goes not to the last, it goes now to the first, and so on. Yeah, yeah, and the second guy goes to the first. So you just swap the order in some sense. Yeah. And then you adjust the signs that it works out. This is how I would explain it, yeah. But honestly, that's the only explanation I can give. I mean, yeah, I because of the non-uniqueness, I think it's really, in some sense, better or cleaner to think of these as non-associative algebra structures, and then you get really uniqueness, right? Yeah. Does this make sense? What I'm trying to say?
Yes. Thank you.
No, you are very welcome. Thank you for your question.
Thank you, Dima and Joerg. Do you have anything else for our speaker? Okay, you know, I just have feeling that I need to teach algebra. It's a good way for me to learn.
Yeah, but honestly, you could teach it even, I mean, you not probably for undergraduates, but in a graduate course, you could teach it in linear algebra more or less. Yeah, I mean, leave certain things out, of course, but yeah, but definitely the first part is only linear algebra, right? And you can motivate then the number theory and at least the composition algebras you could do, right?
Okay.
Yeah. In the second part, when you teach algebra for the graduate students, but honestly, I never did it either because I feel there are so many other things they should learn first, right?
All right.
But what I find a little bit regrettable is that we don't teach the cross product at all in linear algebra. At least here we don't. And as I said, the textbooks I know, I only teach it in Calculus 3, which is fine. I don't mind teaching it in Calculus 3. But first of all, we would save some time in Calculus 3 for other stuff. Yeah. And secondly, I think, yeah, I don't know why this is. I have no idea. Yeah. I think it maybe 40 years ago it was taught, and at a certain point it just got lost. That's my suspicion. Because when I was a student, of course, in Germany, also about this time ago, it was taught, yeah. And I have the feeling that it's not taught in Germany anymore either. I mean, these are the only two countries where I know a little bit what is taught. So I cannot say anything about other countries. But I think the cross product somehow got lost, yeah.
Okay.
But that's just a feeling. I cannot really, I don't have hard evidence for it. Yeah, and I don't know the reason at all. Yeah. Also, geometry in linear algebra got lost, right? When I was a student, it was called linear algebra and analytic geometry. I mean, we did a lot of geometry. Yeah. And now it's just linear algebra, right? Geometry is totally got also lost. Yeah, so it's not only the cross product. I think many things from a linear algebra course, let us say 50 years ago or so, are not taught anymore. And I think they are not taught at all then. I mean, the cross product is because of the calculus, because we need it there. But But the geometry, I mean, the standard classical analytical geometry, I mean, using linear algebra to do geometry, I don't know where this is really taught, except in some very special courses for graduate students, maybe.
So I think maybe we will arrange another time to discuss about how to teach linear algebra and algebra.
Yeah, but
yeah.
I should not be the speaker then, but I would be more than happy to participate, of course.
All right. So I don't see anything else, any questions else for our speaker. So
I hope it was not.
I would like to thank you. Yeah, thank you, Joerg, for interesting talk. And
you're very welcome.
Before we finish this meeting,
thank you. I hope I didn't overwhelm you guys. I'm a little bit worried. But,
because before we finish this meeting, I would like to mention one thing. From the list of participants, I see we have participants from South Alabama, North Alabama, Auburn University, Dakota, and from Vietnam and from Japan. So I'm very happy with that. I think we have very good study today. And we have the next meeting will be in 2 weeks. I will send out another announcement, and we have speaker from Kansas State University.
Okay. Okay. Thank you very much, Hoa. Yeah. Talk to you later. Have a nice day, and thank you to everybody. Yeah.
Thank you.